Welcome to Module 32, which is our last module in this first course on Engineering Vibrations 1 and Introduction to Single Degree of Freedom Systems. Today's learning outcome is just to review the major topics in the course and wrap up the course. And so this is an engineering mechanics course that bridges between engineering science and more engineering design applications. And in engineering mechanics, we generally separate bodies into deformable and rigid bodies. Deformable bodies are dealt with in my four-part series course, Mechanics of Materials, that I published earlier. In rigid bodies, you can have static situations, which were my courses, Introduction to Engineering Mechanics and Applications in Engineering Mechanics. This time we're on the dynamics part of the rigid bodies where we have motion. As I talked about in my two dynamics courses, we talk about kinematics and kinetics, kinematics being the geometrical aspects of the motion and kinetics being the forces, moments being applied, and how that they are changed, the dynamics of the system. And so I had two courses in that field, Engineering Systems in Motion, Two-Dimensional Dynamics, and Engineering Systems, Advanced Engineering Systems in Motion, Three-Dimensional Dynamics. And then the follow-on to that is this four-part series that I'm now providing in vibrations. This is a series of courses in engineering vibrations. We started today, we're finishing up in Engineering Vibrations 1, an Introduction to Single Degree of Freedom Systems. My next course will look at applications in single degree of freedom systems. Then we'll move on to multiple degree of freedom systems. And finally, my fourth course in this series will look at continuous distributed vibration systems. As a general overview of vibrations, this applies throughout all the courses, all four series of courses that I'm going through. We're taking some actual systems, some real-world engineering systems, and we're analyzing, we may be designing it. We have some input to the system because it's vibrating. This can be provided by initial conditions like we saw in this course for free transient vibrations. And in my next course, I'll look at applied forces, harmonic, base excitation, rotating imbalance, and convolution integrals. These can actually be also applied to multiple degree of freedom systems. And once we put that input to the actual system, you observe a response. And what we want to do is model that response, analyze it, perhaps design it better. And so in physically modeling the actual real-world engineering system, we use a physical model, which is composed of masses, springs, and dampers. And as I showed you before, or told you before, the whole world is going to be modeled in this vibrations course by masses, springs, and dampers. And to do that, we make several simplifying assumptions. We look in a single degree of freedom and multiple degree of freedom at lumped characteristics. Later on in the continuous system, they won't be lumped, but we will look at linearity so that we can use the principle of superposition, and it makes the solutions more straightforward. And the systems that I am covering in my courses have constant parameters. There's no change in the parameters as a function of time. So once we come up with that physical model, it may be a single degree of freedom system, as we saw in this course, or it may be a multiple degree of freedom system, which we'll see in my third course. And with that model, we want to come up with a mathematical model of that motion, that vibration. And to do that, we're going to apply Newton-Euler's laws like we did in this course. Later on in the multiple degree of freedom course, I'm going to introduce Lagrange's equations, or energy methods, for coming up with the differential equations. Having that mathematical model, it appears in the form of a differential equation of motion, as we've seen. We can do a numerical input, a mathematical input, I should say, with the same sorts of inputs that we see into the actual system, as shown above, initial conditions, applied force, and on all the all the inputs that can be observed. And finally, we come out with some sort of a mathematical response solution that describes the motion. And we can compare that It can be either a transient response, as we saw in this course, or it can be a forced response, or what we sometimes refer to as a steady state response. And we compare that to the actual response that we observed in the actual real world engineering system. Then we can test, compare, analyze, design. Our model may have made too many assumptions. We may not be getting good results. So we would update the model if necessary and continue the process until we have something that's going to serve our needs in doing better engineering to make better things in the world. And so that's what engineers do. And so with that, the conclusion of the course is I want to congratulate you on completing this course. You've done a great job. This is not easy material. And the summary of this last module is just that we reviewed the major topics in the course. And so I hope to see you in my future courses.